video we are going to talk about powers of the adjacency matrix. So we can use the powers of adjacency matrix to count the number of different edge sequences of length k between any two vertices in the graph. So first of all I will define what an edge sequence is. Then after that we will prove a theorem that is related to the power of the adjacency matrix. So let me start by defining an edge sequence. So the edge sequence is defined as follows. An edge sequence is a sequence of edges in which each edge except the first and the last has one vertex in common with the edge preceding it and one vertex in common with the edge following it. Okay, so let me give an example, then using that example I will make the definition more clear. So let's consider an example of an edge sequence. Okay, so let's consider this graph G. Okay, and here this sequence corresponds to an edge sequence for this graph. So here we can see that this edge sequence starts from vertex V1, then it follows the edge E1 and moves to V2. Okay, then it uses E2 and using E2 it moves to V3. Okay, then from V3 it uses E3 and moves to V4. Okay, and from V4 uses E4 and moves to V2. Okay, and again from V2 it uses E2 and moves to V3, something like this, and from V3 it uses E5 and moves to V5. So this is an example of an edge sequence for this graph. Okay, we can also write this edge sequence by listing only the sequence corresponding to the edges. Okay, so here we can see that the first edge is E1, so E1 can be copied here, E2 next, E3, E4 next, then E2 and E5. So okay, either we can use this one or this as the edge sequence, both are same. So here we can, okay, let me explain the definition using this example. So edge sequence is a sequence of edges in which each edge except the last except the first and the last has one vertex in common with the edge preceding it and one vertex in common with the edge following it. For example, okay, let's consider this edge E2. So edge E2 is preceded by E1 and followed by E3. So let's look at this sequence. So we can see that okay, E2, okay, it is not the first or the last vertex, last edge in this sequence. Okay, so it is in the middle, has one vertex in common with edge preceding it. So the edge preceding E2 is E1. So here the common vertex is V2 and one vertex in common with the edge following it. So the edge following E2 is E3. Okay, and the common vertex is V3. Okay, so again you can see the same thing with this. Okay, this E4. Okay, the edge preceding E4 is E3. So here the common vertex is V4 and the edge following V4 is E2. Okay, and the common vertex is V2. Okay, so that's what an edge sequence is. So an edge sequence is a sequence of edges in which each edge except the first and the last. So in this case this is the first and this is the last. Okay, that okay, these two edges, they don't have any preceding or this has no preceding and this has no following edge. Okay, so okay, except the first and the last has one vertex in common with the edge preceding it and one vertex in common with the edge following it. Okay, so and again a walk or a path in a graph are also examples for Okay, a walk or a path in the graph are also examples of an edge sequence. Okay, so we can replace this edge sequence with the word either a walk or a path. Okay, so let's go and state a theorem related to the power of the adjacency matrix. So the statement reads as follows: if X is the adjacency matrix of a simple graph G, then the ijth entry of the kth power of the adjacency matrix is the number of different edge sequences of length k between vertices v1 and v2. Okay, so we can use this theorem to count the number of distinct edge sequences or number of distinct walks of length k between vertices vi and vj, or the number of distinct paths of length k between vertices vi and vj. Okay, so let's go and prove this theorem. So the proof is by induction, mathematical induction on the parameter k. Okay, so the base case, okay, so for k equal to 1, okay, we can very easily see that the result, it follows from the definition of the adjacency matrix. Okay, it follows from the definition of the adjacency matrix X. Okay, since in this case, if you take the kth power and look at the ijth entry, okay, that is on k is equal to 1, so this is nothing but the ijth entry of the adjacency matrix. So by definition, this is equal to xij. Okay, and this xij is equal to 1 if there is, okay, if there is an edge sequence okay, if xi equal to 1, if there is an edge between vertices vi and vj, and that corresponds to, and this corresponds to, okay, and that corresponds to an edge sequence of length 1. Okay, so and if this is not equal to 1, it is 0. If in that case there is no edge, then no such edge sequence exists. Okay, so we are done with k equal to 1. Okay, so that says the result follows holds for k equal to 1. Okay, let's consider one more base case. Okay, for k equal to 2. So again, if we look at the ijth entry of this matrix, okay, so this is nothing but multiplying the adjacency matrix with itself. Okay, so by the definition of matrix multiplication, okay, this is nothing but summation over all some intermediate vertices okay, x, the I mth entry of the adjacency matrix, okay, this times the mjth entry Okay, and by definition this is equal to m equal to 1 to n. By definition this is equal to x of im times, and this is equal to x of mj. Okay, and this quantity is equal to 1 if and only both of them equal to 1. Okay, and that says the number of arcs of length. Okay, so we can see that this quantity is equal to 1, something like, suppose that this is vi and this is vj and this is our intermediate vertex m. Okay, so this quantity, it is equal to 1 only if there is an edge between va and vm and vm and vj. Okay, and here we are summing over all those intermediate vertices, okay, which looks something like this. Okay, so we are summing over all these m's, and that counts the number and a number of paths between this v1, vi and vj that goes through some intermediate vertex. And here again we can see that the length of these paths is 2. Okay, is 2, 1, 2 edges. Okay, so we are dealing with paths of length 2 here. Okay, so the number of edge sequence of length 2 okay is the number of vertices, these intermediate vertices Vm such that there is an edge joining Vi, vertex Vi and Vm, and from Vi to Vm, and from Vm to Vj. Okay, so the number of edge sequences of length 2 is the number of vertices Vm, okay, these intermediate vertices, such that there is an edge from Vi to Vm and from Vm to Vj. So these two numbers hold that information, okay, by the definition of the adjacency matrix. Okay, and here this is exactly the ijth entry of the square of the adjacency matrix. Okay, so this thing, okay, and this thing is nothing but this is exactly the ijth entry of the adjacency matrix squared, okay, by the definition of matrix multiplication. Okay, and that's what we wrote here. Okay, so the number of edge sequence of length 2 is the number of vertices Vm such that there is an edge from Vi to some intermediate vertex and from Vm to Vj. Okay, and that says this is exactly the ijth entry of x squared. Okay, and it follows from the definition of matrix multiplication. Okay, and that says the result holds for k equal to 2. Okay, so now we are going to prove for a general case. Okay, for a general case when we take the power kth power of the adjacency matrix. Okay, so let's state the induction hypothesis. Okay, so assume that the statement holds for all positive integers less than k. Okay, so assume that it holds for all positive integers, means 1 up to k minus 1. Assume that the statement holds for all positive integers, okay, strictly less than k. Okay, so induction step. So we consider, so what we are going to do is we are going to prove for x to the k. Okay, so consider x to the k and see what is going. Okay, so matrix multiplication is associative, so that says we can write this x to the k as x to the k minus 1 times x. Okay, so we can do the multiplication in this order. Okay, now we can use our induction hypothesis on this part. So this matrix is the k minus 1 power of the adjacency matrix. So we assume that the statement holds for all positive integers less than k. So that says we can use our induction hypothesis here. Okay, and okay, let me rewrite this in a different way. Let's consider the ijth entry of that power. Okay, so that is, if you look at the ijth entry of this kth power, so that is going to be the, so this here we are performing matrix multiplication, so that says that will be something like a summation from m equal to 1 to n. Okay, then we have the first part x to the k minus 1 and take the mth entry of this matrix times the mjth entry of this matrix. Okay, so by the induction hypothesis, okay, we can see that this matrix or the ijth entry, not ijth, imth entry, okay, imth entry of this matrix is the number of distinct edge sequence okay, number of distinct edge sequences of length k minus 1 between vertices vi and vm. And if you look the second part, okay, the mjth entry is the number of edges. Okay, by the definition of adjacency matrix, it is the number of edges between VM, vertices VM and Vj. Okay, so let's look at a fixed m, and then after that we will generalize. Okay, so here we can very easily see that for a fixed m, okay, this product x to the k minus 1 im times x mj is the number of edge sequences from vi to vm, and from this particular product is the number of edge sequences from vi to vj. Okay, we are fixing this m. So this by induction hypothesis we have distinct edge sequence of length k minus 1, okay, plus this edge. Okay, so is the number of edge sequence from vi to vj of length k, okay, k minus 1 by induction hypothesis, and plus 1. So k minus 1 plus 1 is k of length k with this vm as its penultimate vertex. Okay, penultimate vertex. Okay, then this is for a fixed m. So to get for a fixed m, xi is the number of edge sequence from vi to vj of length k with vm as its penultimate vertices. But okay, here this m could be any other vertex. Okay, so we need to sum up all the possible values for m. Okay, so thus summing over every possible values of m, okay, it results in the number of distinct edge sequences from vertex vi to vj of length k. Okay, and that's it. So we proved that the result do holds for an arbitrary k. So the result holds for k also. Okay, so and we are done with the proof, and that says if x is the adjacency matrix of a simple graph G, then x to the k, the ijth entry of this matrix, is the number of different walks or edge sequences of length k between vertices vi and vj.